Open Shortest Path First, OSPF, is a robust link state routing protocol designed to provide faster convergence and better scalability than the older Routing Information Protocol, RIP. It functions by organizing a routing domain into distinct areas, which allows administrators to efficiently manage and control routing update traffic. In this context, a link refers to any router interface, a segment connecting two routers, or a stub network like an Ethernet LAN. Link state information, consisting of the network prefix, length, and cost, is shared across the network to build a complete map of the topology. By focusing on these link states, OSPF ensures that every router has a synchronized view of the network structure. This specific module introduces the fundamental concepts and configurations required to implement OSPF within a single area environment. Like all routing protocols, OSPF relies on specific messages to exchange data, build internal data structures, and process routing algorithms. To maintain an accurate network map, OSPF utilizes 5 distinct packet types: hello, database description, link state request, link state update, and link state acknowledgement. These packets are essential for discovering neighboring routers and ensuring all devices share synchronized topological information. By exchanging these messages, routers can effectively monitor the state of their connections and respond to changes in the network layout. This module details how these components work together to establish and maintain reliable routing paths. Single Area OSPF v2 concepts. OSPF messages are used to create and maintain 3 distinct databases that allow a router to navigate the network efficiently. The adjacency database, viewed via the show IPOSPF neighbor command, maintains a unique list of all neighboring routers with established bidirectional communication. Meanwhile, the link state database, LSDB, serves as the topology table, which is identical for all routers within the same area and represents the entire network map. By running the shortest path first, SPF, algorithm on the LSDB, the router populates its forwarding database or routing table. This unique table contains the best paths for sending packets to specific destinations and can be inspected using the show IP route command. Together, these 3 tables enable OSPF to build a complete, synchronized, and functional routing structure across the domain. OSPF utilizes the Dijkstra shortest path first, SPF algorithm, to process information gathered from the network and determine the most efficient paths. This algorithm calculates the best routes based on the cumulative cost required to reach a specific destination. To do this, the SPF algorithm creates a logical SPF tree by placing the local router at the root and calculating the shortest distance to every other node in the network. The resulting calculations are used to identify the optimal paths, which are then stored in the forwarding database to build the router's routing table. By using this structured approach, OSPF ensures that each router has a clear, mathematically validated map for directing traffic. This process allows the protocol to dynamically adapt to network changes by recalculating the tree whenever the topology is updated. OSPF routers complete a standardized link state routing process to maintain accurate routing information and achieve a state of convergence across the network. The process begins with each router establishing neighbor adjacencies by exchanging hello packets with directly connected routers. Once adjacent, they proceed to exchange link state advertisements, LSAs, which contain information about the router's local links and known costs. These received LSAs are used to build the link state database, LSDB, which serves as a complete topology map of the area. Finally, the router executes the SPF algorithm against the LSDB to calculate the shortest path to all destinations, ultimately allowing it to choose and install the best routes into the routing table. OSPF supports hierarchical routing using areas to make the protocol more efficient and scalable, as an area confines the scope of link state information. All routers within an OSPF area share the same topology data in their link state databases, LSDBs. OSPF can be configured either as single area OSPF, where all routers belong to one area, with best practice dictating the use of Area 0. Alternatively, multi-area OSPF uses multiple areas in a structured hierarchy, where every non-backbone area must connect to the backbone area, Area 0. The routers that connect these different areas are specifically called Area Border Routers, ABRS. Implementing OSPF with a hierarchical, multi-area design offers significant advantages for network efficiency and scaling. First, it results in smaller routing tables, because network addresses can be summarized between different areas, reducing the number of individual entries needed. This design also contributes to a reduced link state update overhead, as smaller areas lessen the processing and memory demands on individual routers. Critically, multi-area OSPF limits the frequency of SPF calculations. Any topology changes are localized within their specific area, preventing link state advertisement LSA flooding from impacting the entire network and preserving network stability. OSPF v3 is essentially the IPv6 counterpart to OSPF v2, designed specifically for exchanging IPv6 routing prefixes to populate the IPv6 routing table. Functionally, it operates much the same as OSPF v2, utilizing the Dijkstra SPF algorithm as its core computation engine to determine the best paths through the network. A key difference is that OSPF v3 uses IPv6 as the network layer transport for communicating with its peers and advertising routes. It is important to note that OSPF v3 runs as a separate and independent process from the IPv4 OSPF v2 protocol, even though their underlying operations are fundamentally the same.